My name is David, but better known as D-Wizzle Weston. I'm a group manager at Microsoft. So my daily job is exactly like an episode of Mr. Roboto. Just hacking stuff, going wild. So I'm going to talk to you a little bit today about how we build security into Windows by hacking it. The goal here is all of you are primarily customers of Microsoft stuff, so we want to peel back the onion, so to say, and show you a little bit about how we make and how we develop security features in Windows. So essentially, the talk's going to go like this. We're going to talk to you a little bit about this new process that I'm very excited about that we call data-driven defense, where we analyze and aggregate attacks coming in to Windows that we can observe through the Microsoft Security Intelligence Graph, and we drive features based on that. In addition, we hack our own stuff. So I'm going to talk to you a little bit about how we run our own red teams against software, which is probably a little different than the conventional kind of infrastructure red teams many of you will be familiar with. And then finally, the proof is in the pudding, so I'm going to show you a lot of the Windows 10, specifically Anniversary Edition features that we've driven based on kind of hacking Windows and observing attacks in the wild. But just a quick introduction of myself. I've been at Microsoft about 9 years, the entire time in Windows security. I own 2 teams at Microsoft. One team hacks the stuffing out of our stuff. The other team is dedicated to Windows Defender Advanced Threat Protection. And so we're building mitigations and detections based on our own discoveries through hacking Windows. And so we're going to talk to you about how that cycle works together. I'm cool with questions if you want to shout stuff out. Otherwise, I'll take stuff at the end. But without further ado, let's jump into it. So the traditional approach to software security, not just at Microsoft, but across the board, is what I would categorize as preventative security. So many of you are probably familiar with sort of various processes around security that Microsoft has published, primarily the SDL, or Secure Development Lifecycle. And the way we had previously secured our products was we would do an analysis while we were writing the code during the engineering cycle, and ultimately the goal was to ship bug-free software. So that's obviously challenging when you're talking about millions and billions of lines of code. So though preventative security has done a lot to improve security since, say, the Windows XP SP2 timeframe when we started it, in the modern day threat landscape, it's probably not sufficient alone. And one of the reasons is the SDL was really tuned towards working with engineering teams. So it was very compartmentalized. If you own component foo, you were only in charge of securing component foo. If you owned component bar, you would focus on the security of bar. If foo and bar don't play well together, that's where the hackers are going to go. And so that kind of component level security is great for building a giant kind of engineering machine, but it probably doesn't reflect real world attacks very well. And so that's kind of the first issue is attackers are agile. They're very adaptive and they're results focused. So if you push down on preventative security in one area, but it's not fully sufficient or you haven't done it across the board, that's obviously where attackers are going to go. The other issue is that the way we treated security previously was we'd focus, Microsoft has control of the Microsoft code. But you as enterprise users probably realize there's a lot of stuff that goes onto the machine. Things like Adobe Flash, maybe Oracle's Java. All that adds up into the threat landscape. So our traditional kind of process didn't really account for the third-party integrations or the additional OEMs that were adding things onto the code. So that was another issue with preventative security. And then finally, since we were focusing primarily on the bugs, right, finding vulnerabilities before we ship them out to enterprises, we were ignoring some of the things that happen after a bug. So what we found over time, and I'm going to share with you some of the results, is that the best place to mount a defense is not necessarily in eradicating all of the vulnerabilities, which is a very complex problem, but in developing mitigations and defenses that assume vulnerabilities are there, but make those vulnerabilities harder to convert into a real-world attack. And that's actually reflected in the market. I'm not sure how many of you know, but there's actually a market out there for exploits, right? There are commercial companies who are maybe selling to enterprises or governments fully weaponized exploitable code that can take control of a machine, of a browser, of a word processor, et cetera. And one of the pieces of evidence we see in this market value is that vulnerabilities are about 10 times cheaper in the open market than a fully weaponized exploit. And the reason is software defenses, not vulnerability eradication, is what actually adds complexity and cost to attackers. So if you can buy a vulnerability for $5,000, an exploit of that vulnerability is going to cost you anywhere from $50,000 to $100,000. And so by focusing on the cheapest part of that economic chain, which is that initial vulnerability, we're not doing our best, to disrupt that market. The other thing that we noticed over time is that another place that preventative security, that traditional approach, wasn't working well was in actually disrupting what attackers are doing. So one of the things I mentioned my team does on a day-to-day basis is we look into so-called APTs, or advanced persistent threats. Maybe a zero-day, maybe a particular group has a certain tool set or a template that they've invested in over time. They've actually built it like an engineering team. They probably, have Git check-ins and TFS, and they got, Agile, Scrum stuff up on the board, and they're building software libraries to go and hack people across the globe. And those are large investments. Perhaps they created a JavaScript or an ActionScript library that makes exploitation very cheap. When you're focusing only on the vulnerabilities, which are just an input into there, you're not disrupting that huge investment. And what we found over time is when we actually targeted breaking these large investments from real-world attackers is that they had to go back to the drawing board. So maybe they had invested 3 years in an SDK for a Flash exploit, and in a couple of days of engineering time and a new patch, we break that completely. And now they have got to go back to the drawing board and develop capabilities. The problem with preventative security is it's not accounting at all for that. And then finally, the toughest part about a strategy that's just trying to find vulnerabilities and when we ship is we never really know how effective we were. And let me explain what I mean by that. You could have a vulnerability discovery program, 20 bug bounties. You might find 99.9% of the bugs. But in that 0.1%, if that's 15 attacks on large enterprise customers, you never know if you did a good job. It's really a losing game. You could do almost a nearly perfect job and still be seen as a not very effective security product. So over time, what we've done is we haven't at all scrapped preventative security. It's still a huge part of our strategy. But we've realized that assuming breach, and in the context of software security, that means assuming there's going to be vulnerabilities, we need to build infrastructure and features into the Windows platform that essentially assume that a vulnerability is there and try to break basically weaponization of that exploit, of that vulnerability. So how does that work? Data-driven defense. So the first thing we do is we need to have really excellent analysis of the problem. So the way we do that is every exploit that Microsoft can get its hands on, and obviously we have a vast network of telemetry, we have a lot of industry partners, maybe some of you in the room, who exchange data with us, but we are constantly building, pruning, and building an analysis set of how attacks work in practice. And from that set of attacks, we essentially pull out invariants. So if we see 10 different attack groups are using technique Y, then that is a very good place to potentially mount a defense. And I'm going to give you examples of where we've kind of torn apart some of the common exploitation in zero-day exploit sites and built those types of things. And what we're looking for in this analysis is really opportunities to build the next great security feature. You've been at this conference now for 4 days. You've probably seen a lot of those features. A lot of them are influenced by this kind of, frankly, in some cases, monotonous analysis that's absolutely necessary. Actually, the way I describe this analysis is almost like zoology. Like, we look at the exploit, we write down some trivial stuff, and we're cataloging it over and over again. It's a lot like a zoologist who's maybe watching a monkey eat a banana or go to the bathroom. You're just cataloging that stuff. So that grunt work, in the end, though, shows you trends that you can use to identify opportunities to build features. The other significant change we made as Microsoft is, in the past, security engineers were sort of almost functioned as independent consultants at Microsoft. So a security person might find a problem, and they would go to a team at Microsoft and say, can you please fix this problem? And obviously, that team's got a lot of priorities, maybe feature sets that you as customers are requesting, maybe they're fixing things, maybe they're trying to make things faster. And since they're not security experts, they may not really internalize how important a security feature is. So what we started to do was pull in traditional software engineers into the security group who could actually build those things. So once we had done a comprehensive analysis of a data set, We then had our own engineers in the security group who could just go and build things, and then we'd show up at the feature team and say, here's your code. And it solves all problems X, Y, and Z. And they were like, cool, this is awesome. And so we found a much better way to kind of work within Microsoft to make sure that we were shipping the most advanced and most disruptive features possible. And then the final part of that, which from my perspective is the most fun, is we evaluate our own defenses. So if we build, say, a buffer overflow protection or a heap spray protection or some other specific attack protection, we want to know it works before we go out at a conference like this and tell all of you that this is the good stuff. Well, how do we do that? We now go ahead and just write exploits and we build our own attacks against Windows. So I've got a group of guys and gals who are some of the most skilled in the world, and their job on a daily basis is to take code from my other engineers and see if they can essentially bypass it. And by bypassing it, I don't mean just looking for a vulnerability that's kind of abstract, but literally build a weaponized attack that's on par with some of the stuff you see in the news so that we can then deconstruct it and make sure that we resolve those gaps. So that evaluation component is new and very critical to the success. So I wanted to just kind of run you through how this works in practice. So I mentioned security telemetry, things like Windows Defender and ATP are a critical source of reports. So if we see, say, a new exploit out there in the wild, we can pull it in and do some analysis. We also, as Microsoft, frankly, we're responsible for a good number of the vulnerabilities that are in our own products. So we're getting reports in there, we're doing the analysis there. We use threat intelligence partnerships and threat intelligence that we cultivate through Windows Defender Advanced Threat Protection to generate potential signals into this system. And then obviously we've got very good systems for monitoring open source intelligence or social media. The other thing that obviously I talked about a bit is we have our own red team operations. So we're able to get data on the way that our own internal teams are breaking our software. We're able to use that to kind of identify various trends. That goes into this multi-dimensional exploit analysis, which looks at, say, the root cause. What is the particular software flaw that's being exploited, and how often is that used in a set of exploits? We also look at techniques. So reading through security blogs, you may have heard of techniques like heap spraying or use after free. We look at these various exploit techniques and we catalog how frequently they're used, in what contexts, against what components. Additionally, we look at the components themselves. Is this component becoming disproportionately attacked? Is there something wrong with it that we can identify as a potential source for investment? And then finally, we want to look at, through this data, how well is the stuff that we've actually shipped out there, whether that's something like Device Guard, whether that's Control Flow Guard, which is another exploit mitigation feature that's been built into Windows since 8.1. How well are these security features working? That all goes into a big data set that we use to then generate regular threats and insights. And we use these reports to actually identify what we're going to go build in the next version of Windows. And at that point, by the time we have that report, we're very confident that these features will, say, disrupt the most common trends from things like exploit kits that are used to distribute ransomware, or potentially advanced targeted attacks. So let's look a little bit about how well this is working. So if you look at this chart, and I'm going to look at your way, on the left-hand side, what we're seeing is that vulnerabilities in Microsoft software and software overall are growing. It's a fairly steep chart there. So there are more and more vulnerabilities being reported than ever. So if you were just to look at this isolated data source, which is actually a very common data source that people use to judge security, you would think things are pretty bad, right? Tons of bugs, tons of security vulnerabilities, the world is burning. But what we're actually seeing in practice is on the right-hand side of the chart, which is the number of times those vulnerabilities are converted into actual attacks that are possible of targeting a customer, is dramatically dropping. Considerably, right? We're going from, maybe a peak in 2010 to where in 2015, it's a very small elite number of people who actually have the technical skills, resources to develop a weaponized exploit against Windows. And so thinking back on the preventative security side, we wanted to understand if there are more bugs than ever, and there are more vulnerabilities than ever, what in practice is going on that's preventing attacks from growing at the same rate. And our view is that the mitigation technology that we're building into Windows, Device Guard, Address Space Layout Randomization, Control Flow Guard, and various other features are making those vulnerabilities that are potential risks and preventing them from actually becoming actualized risks. And so we wanted to harness that. So here's a really good example of where we were able to, in practice, analyze a data set and develop a set of mitigations for it. How many of you are familiar with Adobe Flash? Probably most of you. How many of you are familiar with kind of the security history of Adobe Flash recently, right? They've had some issues there. So one of the things we did, based on our own internal success, is we started to work with Adobe to kind of test out our generalized process. So we thought we were onto something internally. We were doing pretty well, and I'm going to show you some Microsoft results. But we thought, hey, let's test this out, and let's see if we can use this same process to work with Adobe. And so one of the things we did in the Flash section is we looked at their data sets. And you can see, again, on the left-hand side here, a chart of the most frequently used exploit mitigation or exploit techniques for Adobe Flash over the last 2 to 3 years. And what we identified there was upwards of 85% of the in-the-wild zero-day exploits, whether those were exploit kits distributing ransomware or targeted attacks, were using something we call, and this is a little bit technical, but vector length corruption. And basically, that technique was almost universal. So when sitting down with our partners at Adobe and saying, what could we do to improve Flash security? Because Microsoft does distribute Flash in box. We have a keen partnership and a mutually shared interest in protecting customers. We looked at byte array and vector length as a place that we could go ahead and build something. So based on that, we worked with Adobe to ship what we call a vector length integrity protection, or something that basically monitors that structure in memory and safely terminates the program if that's corrupted. And we ship that out to customers. And based on that, I don't have updated stats, but we're seeing upwards of 50% reduction in zero-day exploits against Flash, just based on some very straightforward data analysis and mitigation implementation. So that's, in our opinion, a real validation of the strategy. We were able to take it from Microsoft and apply it to Adobe as well. Additionally, we did something very similar for Internet Explorer. So again, prior to Flash kind of being the place where attackers were focused, Internet Explorer back in 2014 was a major focus of targeted attacks. So if you look at this kind of timeline chart I've got here, in the first part of 2014, we were frankly in bad shape with Internet Explorer security. We had 4 0 days in the span of 3 months. The DHS was kind of out there saying, we don't necessarily recommend Internet Explorer right now because it's a security issue, et cetera. It's also ironic because I got the job like the next day after that happened. And so what we did is we took a different tact. We did something very similar to what I just showed you what we did with Adobe Flash. Is we started looking at, in practice, what were these attackers doing? What were the techniques they were using, and what could we do? Our traditional approach probably would have been go run fuzzing, go do more code review, go try to find all the vulnerabilities. But frankly, we had been doing that for some time, and it wasn't working in the case of Internet Explorer, partially because it's fairly legacy code and it's fairly complex and hard to maintain. So instead, what you see here in the green is we did something unprecedented for Microsoft, which is we looked at the techniques and those things that attackers had invested in. We developed various techniques to break them, and we started shipping them out month after month in security updates. And what we saw was an absolutely dramatic reduction in 0 days. So in 2014, we had 135 days during that year where there was a 0-day in the wild that we didn't have a Microsoft patch for. After this series of mitigations were shipped, we reduced that number to a third the next year. So we had a dramatic impact in Microsoft Internet Explorer. And again, we thought we were onto something with this mitigation stuff. So the next question was, so we know this worked for Adobe. We know it worked pretty well for Internet Explorer. We think we're onto something. How do we formalize this and make this just part of the way we do business? The other thing we were concerned with is, if you notice, the vast majority of those security features we built there were based on in-the-wild attacks, which is not ideal. You don't want to wait to have the great idea until somebody gets hacked. You want to have that idea before they get hacked. And so we wanted to move away from a reactive stance where we're just kind of waiting for 0 days to happen, doing the analysis, and then coming up with that next feature, and instead do that proactively. So in the software security community, we looked at what was happening, especially at Microsoft in the services realm. So we've got some really awesome security teams in the Microsoft Azure Cloud Group, in Office 365, who had been doing these kind of war games or red team exercises for some time. And they had a mantra that was assume breach, which was assume attackers can get in, and the goal from a defensive standpoint is to detect them as fast as possible and shut them out. And you do that by having excellent layered defense, you do that by having excellent logging and detection, et cetera. And so we looked at and said, could we apply that to the software model, which is, could we take a threat emulation team, go build 0-day exploits against our own stuff, and you have to realize that's a pretty radical notion here at Microsoft, and then use that to drive some of these cool security features that you'd seen in that previous chart. And so our hypothesis is we can use assume breach for the Windows client in the same way we've been using it successfully for O365 in Azure, and you can use that to drive effective security feature development, which we know from our data analysis is the key element in making our products more secure. So we were able to, over time, again, do more and more of this emulation bit by bit. And one of the places that we kind of tested this hypothesis was in the so-called Pwn2Own competition. How many of you are familiar with this kind of world-class hacking competition that happens once a year? Well, for those of you that are not, there is a security conference every year in Vancouver, Canada called CanSec West, and they have a kind of world hacking competition that they call Pwn2Own. And the concept of this is they invite white hat hackers, so hackers who are professionals that mostly work at technology companies, and they demonstrate their skills by hacking some of the top browsers. So every year there's generally Microsoft Internet Explorer, Microsoft Edge is there, and it's a potential prize to be hacked. Often you'll see something like Apple Safari and Chrome. And the goal there is these white hat hackers come and exploit things. They kind of win points, and it drives a kind of a competition. And then they privately share the details with us, and we use that information to kind of assess how we can improve. And what we found over time is that this competition, just a few days a year, was one of the best sources of intelligence because these folks were so good and so friendly to us that they were helping us to build our own products. And so what I did is I went to management and I simply said, I want to do this all year long. And after a year of them telling me I was crazy, they finally let me do it. They finally let me put together a team of crack hackers. And we call that the Windows and Devices Red Team, or the Offensive Security Research Team. And this team is goaled around a few things. We want to model real-world attacks. So, for example, many of you have heard about the new security features here at the conference. So things like Device Guard, App Locker, various things related to our mobile devices, hypervisors, et cetera. All of those things undergo real-world penetration testing. So my team essentially tries to hack it and break it before it reaches you folks. And oftentimes we do. We do break it. We take a round around it and we fix it. And so by the time it gets to you, it's been through 3 or 4 rounds of this kind of world-class threat emulation, the same kinds of things that will happen in high-threat environments that are shipped to you. And so we usually have pretty good kind of views on what that's able to do. The second thing that we do besides modeling those real-world attacks is we're able to actually build hardcore measurements of the cost of hacking something. So for example, if we hack scenario foo and it takes us 100 days, and we go back and do a round of basically adding security features, adding additional layers, the next time we try to hack it, it should be 500 days. And so we are able to maintain kind of these goalposts for all of the key security features that we ship to you, where we sort of understand exactly the cost to hack it, at least in our environments. The other thing we're able to do is we're able to kind of judge essentially what people will go after. So if a component is fairly complicated, we may know these 2 or 3 components are particularly problematic, and we can start to build detections around them. So a lot of the end-to-end attacks that my team builds on the red side will immediately be transferred into things like Windows Defender ATP. So we actually have additional insurance policies, logging, and detection that sort of assume breach mentality built into Windows as a whole. And then finally, one of the great things we're able to do is kind of show over time how that's reflected. So many of you probably seen the recent iPhone hack, right? There was an iPhone hack in the wild. We've done those sorts of things internally for a while, so we know exactly who we should contact, what are the right types of logging and infrastructure we need to respond to an incident. So we have great security proactive and response infrastructure set up before we ever ship a product. So we get a ton of value out of this kind of threat emulation. And so probably the best outcomes I can show you are the set of features I'm going to kind of walk you through that we've built based on this. But we've been operating now for over a year. We found many, many new types of techniques that we're able to mitigate long before they ever reached customers or attackers found them. And we've been able to drive a lot of this, as I said, into Windows Defender and Defender ATP to do detection. So it's moved from sort of a fringe or a prototype idea just a few years ago into a core way we do business. And it's right there with our SDL and vulnerability discovery programs as kind of a primary pillar. And so without further ado, rather than kind of describe to you some of the attacks which are obviously sensitive, I'm going to do one better and just kind of show you some of the features and outcomes that we've got out of red teaming Windows. So this is our core strategy for mitigation development. The first one is we want to make it difficult and costly to find vulnerabilities. That's that proactive piece. Our tactics are we want to eliminate entire classes of vulnerabilities so they can no longer be exploited. We want to break exploitation techniques, or we want to contain them using things like hardware-based software isolation or app container isolation technology. And then finally, we want to make sure that we can patch and respond to attacks incredibly quickly. Those four pillars in combination compose our strategy. So I'm just one person here representing the work of possibly hundreds of people across Windows. I want to make sure I acknowledge I'm just kind of the mouthpiece for the hard work of a lot of folks. And so you can follow up on that slide later offline. So let's talk first about what kinds of things we're doing to eliminate classes of vulnerabilities. And again, the goal here is to make it hard to find kind of the raw material to build an exploit to begin with. So as I mentioned, we closely study the root cause of vulnerabilities, and we convert them into particular classes so that we can monitor trends. And what we see is those trends change over time. So if you look back in 2006, 2007, the primary root cause of most exploits and most vulnerabilities impacting Microsoft was something we call stack corruption. So if you're familiar with software at all, you know that it's very simple in some cases as a developer to make a mistake that results in something called a stack-based buffer overflow. And in 2006 and 2007, the state of the art for attackers was to find those buffer overflows and exploit them. And a real success story over time has been we've virtually eradicated that class of vulnerability. If you look at this chart here, it essentially doesn't exist. Now that doesn't mean that attackers don't move to other places. So what we saw was a steep shift from this stack-based buffer overflow issues into attacking use after free issues, mostly because we pushed down in that place so folks pop up somewhere else. And of course, by studying that trend, we then introduced a series of mitigations against these so-called use after free issues. And then finally, we see additional trends that we're working on now to mitigate, which are related to things like heap out-of-bound reads, type confusion, or DLL planting. These are all different classes of software flaws that we see in practice converted into attacks. So let's talk first about a feature in Microsoft Edge and Internet Explorer that was designed to address that use after free trend in vulnerabilities. So the vast majority of security issues in Internet Explorer traditionally what we call use after freeze. So this is a fairly technical description, but I'll try to simplify it a bit. In software that's implemented in C++, you have what's called an object, and that object needs to maintain a reference so that the memory is kept alive. When a developer makes a mistake and doesn't keep a reference there, an attacker has the opportunity to fill that memory with some content of their choosing. And they often do that through a JavaScript program that we call an exploit. And then when the normal flow of the program resumes, it's calling into this attacker supplied data, which essentially allows the attacker to run any any code they would like. And so the way that we've addressed that issue over time is we've simply removed the need for our developers who are working in the browser to manually do anything to kind of maintain this state relationship. Instead, we've introduced what's called a garbage collector that we call a memgc, or memory garbage collector, that simply tracks all those references automatically and keeps memory alive if a reference exists at all in memory. And while that's a fairly technical description of what's going on under the hood, in practice what we've seen is it's reduced use after freeze dramatically to essentially a very small portion of what it existed in the past. So the way to think about it from a customer perspective is we took the most common class of exploits and vulnerabilities using exploits, and we wiped it out. We started shipping that last year in Internet Explorer 11, and it's been there since day one in Microsoft Edge, and it's one of our most valuable security mitigations, and it's fairly unparalleled in any other browser. Additionally, another class that we looked at back in 2014 is what we call type confusion. And again, fairly technical description here, but in C++ you have different types, and if one type is mistakenly applied to a different type, an attacker will have an opportunity to sort of control that object in memory, and again, executes arbitrary code. And so by breaking those down into various classes and looking at the different cases and vulnerabilities, we were able to go through the code and simply make changes that prevent these kind of type confusion issues. And again, we've seen a dramatic reduction in type confusion as a class, which has resulted in increased security for both Edge and Internet Explorer. Finally, a particularly interesting mitigation that I would say is just sort of built into Edge from day one is what we call attack surface reduction. So many of you are familiar with the classic IE issues of toolbars or browser helper objects or all this sort of legacy stuff like VML. I see a lot of nods out there. So the good part is by simply reducing that stuff and removing it from Microsoft Edge, there's tons and tons and tons of old code that frankly likely had latent vulnerabilities that are gone. So by removing that stuff, we sort of clean sweep everything, and we start with a brand new browser that's got a significantly lower attack profile and therefore less things to attack. So from a vulnerability perspective, some of the worst offenders of latent issues are simply removed complete from Microsoft Edge, leading to a significantly reduced amount of vulnerabilities that are reported in general applying to Edge. So simply by moving to a standards-based browser and getting more lean and mean, we've gained a lot of security as a result. So that's kind of some of the work that we've done, at least through the Anniversary Edition, in removing vulnerabilities through new security features. Now I'm going to talk to you about how we are breaking exploit techniques that we see in practice used in the wild. So exploiting vulnerabilities, as I said, back in 2003 or so, used to be incredibly simple. Probably anybody with a little bit of a background in computer science could build something in a weekend with a particular vulnerability. And the script previously was something like trigger a stack-based buffer overrun, take control of the stack address, and simply redirect it to some injected code. Again, fairly simple. Somebody could pick a book up maybe at Barnes & Noble or something like that and sort of build this over a weekend. I want to sort of take you through a journey of how incredibly difficult that's become over time. So in order to address this issue, back in Windows Vista, we introduced something called address space layout randomization. And the way that worked is we simply scrambled or randomized in memory where particular code was. So even if an attacker could say, take control of a return address, they had no idea where to redirect it because it's random every time. So that was a huge breakthrough and broke a bunch of stuff. Now, attackers address that through various means. So, for example, in the stack case, they may have started to focus on vulnerabilities that were, DLLs that were not randomized, or various pieces of code in memory that were in predictable locations. And so the way we addressed that over time was we no longer allowed you to load DLLs in memory that were not scrambled or protected through randomization. And so what we've seen over time is there's this sort of tit for tat, which is attackers get in a position where they simply have a script that makes it very simple to create an exploit. we come back around and sort of change the game on them, and then maybe they have a fundamental breakthrough that allows them to sort of switch it back, and so we've gone back and forth. But where we think we are now is at a point where we've sort of narrowed that funnel down to a few very well-funded and technical attackers who can build an exploit. And so the script today moved from maybe those 2 or 3 simple elements to a full-featured attack stack. So in order to develop an exploit at this point, you've got to bypass address space layout randomization. You've got to create what we call a read-write primitive so you can read across memory or write across memory. You've got to bypass our anti-ROP mitigations, et cetera, et cetera. And this sort of huge stacked and layered protection strategy is what we think is driving that funnel, which I showed you previously, which is vulnerabilities are skyrocketing, but the actual attacks in practice are reducing to just a few, and it's because only a few folks and only a few organizations out there are capable of bypassing this full stack. So let's talk a little bit more about the exploit mitigations that we have in user mode. So again, this is another interesting one that probably isn't intuitive, but by moving to 64-bit browsing in the Edge browser, which we were the first browser to do that, we actually broke a fundamental technique in exploitation. So one of the ways that attackers seek to bypass address space layout randomization is by simply exhausting memory, so no matter where they jump to, their code is there. So there's only so many places we can fit code in a 32-bit address space, so if the attacker simply exhausts all of memory, by chance their code will be somewhere if they choose to jump to it. And so here's a simple illustration of IE, which runs 32-bit by default. When a heap spray attack is executed, the entire memory is filled up in a very short amount of time, seconds. That same attack in 64-bit address space in browsers like Microsoft Edge looks like this. So that entire white space, if the attacker is to sort of randomly jump to a place in memory and they jump into that white space, that attack is foiled and is going to break. And that's something we shipped back in the original version, our original edition of Windows 10 in Edge, and is a significant protection against a fundamental technique, which is heap spraying. Control Flow Guard is another technology which we shipped back in 2014 in Windows 8.1 Update 3. And Control Flow Guard targets the fact that modern exploits use a technique we call return-oriented programming. And the concept of return-oriented programming is that we've restricted the ability for attackers to introduce say, new executable code or predictable executable code. So instead, what they're able to do is stitch together various fragments in memory through a technique we call return-oriented programming to build an attack out of the instructions that exist in memory. And this is a technique that back in 2014 we saw in upwards of 80 to 90% of exploits that appeared in the wild. And in order to address that, we reduced the ability for attackers to simply redirect to arbitrary instructions in memory. The way we did that is we augmented our compilers, so the Visual Studio compilers that are also used to compile Windows and are used by third parties like Adobe to compile Flash. We made it such that the compiler emits a valid set of places to jump in memory at compile time. And then Windows was enlightened to take that information out of the executable and enforce it at runtime. And so what that means is, even if an attacker can get control of a process and is attempting to, say, redirect it to a useful API, maybe write a file, create a process, allocate it in the executable page, if that's not known in the original DNA of the program as a valid location, we simply stop the process and kill it. And so this control flow enforcement approach, or control flow integrity, has been a fundamental breakthrough, and we have seen almost no activity bypassing this in the wild. It's been incredibly effective at breaking a fundamental technique, and it's something that's just there since Windows 8.1. Every binary on the system is compiled with Control Flow Guard as part of the Windows build process, and it's enforcing that at runtime. There's a series of enhancements over time that we've also made to this, and this is basically a call out to the fact that we have a number of bounty programs at Microsoft where we invite people, not just our internal red teams, but our external folks, to go ahead and report things to us. So we had a series of potential bypasses in control flow guard that were reported to us through our Blue Hat mitigation bounty that we've been able to address over time. And those mitigations have continued to shore up our control flow guard investment and make it what we think is the premier anti-return-oriented programming or anti-ROP mitigation out there. An additional mitigation that we've introduced in Microsoft Edge is, again, attacking a fundamental technique that we see often in process, and that is something we call code integrity and image load restrictions. And so what we've done in Microsoft Edge is we've focused on the fact that one of the things attackers do frequently is they get control of the process, and then they want to load remote DLL or remote code. And since Microsoft Edge was built from the ground up as kind of a redesigned browser, we took advantage of the legacy restrictions being lifted and made sure that we signed every binary that was ever intended to be loaded into Microsoft Edge. And so what that meant is now even if an attacker was to somehow get past all of those exploit mitigations I showed you previously and wanted to load untrusted code or was doing something like DLL injection into Microsoft Edge, it actually looks at every single DLL that's going to be loaded or every kind of component of code and ensures it's signed by Microsoft. And if it's not, it simply prevents it from loading. And so unless an attacker has completely compromised an infrastructure and found some way to get code signed, there's simply no way for them to load a DLL in Edge, which is, again, a formidable attack mitigation. Additionally, Microsoft has introduced a series of code integrity restrictions. And so we call this dynamic code restrictions. And if you're familiar with the iOS or iPhone model, there's some parallels here. So what this model says is, or this mitigation does, is it prevents an attacker from creating any new code on the fly. So again, if you think back to our previous script that we introduced, the goal of an attacker is ultimately to get arbitrary code running in the process, right? That code is going to have the DNA of their attack. And so what we found is if we simply are able to restrict any new code from ever being created in a process by implementing what we call dynamic code restrictions, that we're able to break nearly every attack out there today which relies on that. And so in Windows 10, we allow code to simply opt into a set of mitigations through either an API or by setting some various registry restrictions that simply prevent any new code from being introduced. So an attacker, if they were to get control of that process, would not be able to generate new code. They'd have to sort of hop around in memory or do some very nifty tricks enabled to bypass this. And so this is actually quite similar to some of the features you might be familiar with in the iOS or the Apple security model. And that's actually been available in Windows since 8.1. And it's something that we're aggressively looking at turning on across the system. Now, there is a challenge, which is a lot of our interpreted script runtimes, JavaScript, CLR, et cetera, rely on a process we call JITting, right, which is just-in-time compilation to generate new code on the fly. So currently, those processes would be incompatible with a mitigation like dynamic code restrictions, but that's something we're working on addressing. And where folks who maybe own line of business apps here or work on service development, this is a very viable mitigation and something you should consider enabling today. So let's now talk a little bit about kernel. So we talked kind of about the user land space in Windows, but we've seen an increase of attacks in kernel, especially as we've developed new and more isolation technologies in Windows. In fact, when we talked about Windows Defender Application Guard, one of its primary security properties, and that's something we introduced here at the show, one of its primary security properties is the ability to contain attacks that are focusing on the kernel. But over time, we've also been shoring up basically a number of security features in the kernel that make exploitation harder. And so let's talk about a few of those. The first is Microsoft virtualization-based security. You've probably heard a lot here at the conference and maybe at previous introductions into Windows 10 about how VBS makes pass the hash and other credential attacks harder by isolating credentials and other secrets from even a kernel mode attacker. But one of the things that's not incredibly well understood is how powerful this is at preventing exploits overall. So one of the first things I want to talk about is by creating this extra layer of kernel, or what we call the secure kernel, or SK, we're able to create a supervisory position for code that wants to analyze or enforce security properties on the kernel. So let me give you an example. We've had for some time a technology in Windows called PatchGuard. And what PatchGuard is designed to do is to prevent both OEMs and rootkits and things like that from modifying in the kernel in a way that would be destructive to the user, either causing stability issues or maybe developing hooks to do introspection or basically stealth attacks against the particular machine. The challenge with HyperGuard is traditionally kernel was the highest level of privilege in the system. So if an attacker got to kernel, he was running at the same privilege level as the highest privilege code in Windows. That's a problem because it's kind of hard for me to be an enforcer if I'm running at the same level, privilege level as the attacker. And so what we were able to do by introducing virtualization-based security was create a concept of a more supervisory privileged layer. And so we actually call that, if you're familiar with the sort of rings in Windows, right? User mode is ring 3, kernel mode is ring 0. We've created what we call a ring -1. And one of the things we moved into this ring -1 is PatchGuard, and because it's now running in the hypervisor, we've changed the name to HyperGuard. And so HyperGuard is now in a very effective position to monitor key security points in the kernel and determine if they've been modified in a malicious way. And if they are, again, shut down the machine. So one of the additional checks that we've been able to add into HyperGuard is the ability to monitor certain registers that were enforcing the exploit mitigation. So an example of an exploit mitigation that we'd previously developed is SMEP. And what SMEP does is it prevents a kernel mode attacker from redirecting to, say, a piece of code running in user mode. The problem with SMEP traditionally is once you're in kernel, it's sort of hard to enforce any kind of security policy. But by moving this code into HyperGuard, we're now able to be in a position where previously mitigations that were not durable or had known bypasses are now strengthened because the HyperGuard can monitor them and prevent code execution that would cause issues there. Additionally, as I talked about in user mode, one of the end goals for any particular exploit attack or targeted attack is to get arbitrary code running. And what we did in virtualization-based security was introduce this concept of HVCI, or Hypervisor Enforced Code Integrity. So when you've turned on VBS onto a Windows 10 endpoint, we're simply preventing any unknown process, even a kernel exploit, from creating new executable code in the kernel, which makes it extremely difficult or possibly impossible to create a rootkit when HVCI is enabled. And so one of the reasons I wanted to talk to folks about this is we've done a pretty good job of talking to you about how virtualization-based security powers various code integrity policies on things like device guard, as well as prevents hash-to-hash with technologies like credential guard. But there are a number of powerful security properties that are enforced against kernel mode exploits simply by turning in VBS, which is included in most of the Windows Enterprise endpoint licenses that you have available today. Additionally, I talked to you a bit previously in the user mode context about how important code and data randomization is to prevent attacks. Again, realize that when an attacker gets control of a process, or in this case the kernel, the first thing they want to do is identify locations to modify or locations to redirect execution to. So making sure that randomization is sufficiently entropic is a key security property that needs to be enforced. Now, one of the difficult things is when Windows was initially developed, it wasn't developed with this concept of randomization, right? This was in the early days before we had so many user mode or even kernel mode attacks. And so while we have systematically continued to add address space layout randomization and other randomization technologies in the kernel, it wasn't until Anniversary Edition where we sort of nearly completed that work, which is there is a particularly sensitive place in kernel called the page table that controls all the address mappings in kernel. And so previously that wasn't randomized, or the structures in the page table weren't randomized. So if an attacker got control of the kernel, despite what we did in other places, if they found the page table, which is at a predictable location, they could modify that and sufficiently access an attack. What we've done in Anniversary Edition under the hood is increase the randomization of structures in kernel like page tables and made that significantly harder for an attacker to identify and address. So that's a really cool mitigation. So Many of you are familiar with Microsoft's Emmet. Can I get a show of hands if you've heard of Emmet before? And that's our kind of for free component that's an add-on to previous versions of Windows. One of the things I wanted to point you to is that all of the cool mitigations I've showed you today are actually available and can be enabled in Windows through registry keys. So if you've got the ability to push registry keys through your GPO and you want to modify and harden your environment, you can simply go to that AKA MS link below, look into each of these mitigations, and actually turn this on in Windows 10 by default. Our view of Windows 10 is that it has a dramatically effective set of mitigations. It's an incredibly hardened system, and you can harden it more by simply turning on some of these optional features into the processes in your kind of enterprise deployment. And so I want to move on now to containing damage and preventing persistence. Recall kind of the process we're going through here is we want to stop you from finding bugs. If you find bugs, we want to stop you from weaponizing an exploit through our exploit mitigations. And if you get through that trap, then we want to isolate you and contain you within a sandbox. So let's talk a little bit about what we're doing there. So App Container is our fundamental sandbox technology in Windows. It was actually initially introduced in Windows 8 to support our new app model, Store Apps, or UWPs. And so we moved away from the previous model, which was a Win32 process, kind of running at conventional elevation levels, could essentially modify anything on the system, right? Access your data and documents, drive network traffic, potentially access your credentials, very little isolation. So in Windows 8, we introduced a capabilities model that restricted what a particular app could do. So if you went into the store and looked at an app, it would be very explicit and declarative about what it can and can't do. Can it access your videos or music? Can it access documents, et cetera? That's all driven by the fact that the application is sandboxed and thus has only the permissions in which you explicitly grant to it. That was great. Over time, we've been able to harness that technology for other constructs in Windows besides Store Apps. So one critical area in which we've made an improvement is in font parsing. So historically, maybe over the last 4 to 5 years, there's been a number of in-the-wild attacks that targeted our legacy font parsing, our component that takes a font and installs it onto the system. There's been a number of flaws in that. And one of the reasons that was attractive to attackers is, one, much of it is kind of this old legacy code that was potentially developed, before we had such a focus on security. And second, it was running in the kernel. So if you did create an exploit, you were right there at that highest privilege level. And so in order to address that, what we did is we took those legacy components and we moved them into userland, which on its own is a great improvement because it means in the worst case scenario, if there is a font exploit, you're now not in kernel. But we did one better, which is we put it in a very locked down environment in the App Container sandbox. And so in Windows 10, all untrusted fonts coming from the internet are actually parsed in this highly isolated environment, thus reducing the potential impact of any font exploit, which is a major win. The second area that we've done some interesting things is we took Microsoft Edge and we got rid of the older sort of legacy Internet Explorer sandbox, which had some compatibility restrictions, and we created a completely new isolation model. And so what we did is we leveraged the App Container sandbox, and we put all Edge rendering. So when you're looking at images from the internet, JavaScript, all sorts of arbitrary content, that's actually happening in a highly locked down browser rendering process. That's great. We actually use multiple app containers. So all renderers are in their own app container, and then we have a slightly more privileged component in there called the manager, and that's in its own app container. That's great. They can't interfere with each other. If there is a potential exploit in Edge, it's constrained to a very small set of privileges. And then in Anniversary, we did one better, which is we took Adobe Flash, which was previously in a shared app container in this content process, and we put it in its own extremely locked down process. So now you've got these 3 layers of sandbox privileges in a single browser. And so we're able to enforce the principle of least privilege there, which is Flash only gets access to the specific folders or files, et cetera, that it needs access to. And so in the event that there is a Flash exploit, it's very likely that the ability for an attacker to do much to damage a system is highly constrained. We think that's huge. And then Yet again, you can tell I'm pretty excited about some of the stuff we have in here. We implemented another feature in Anniversary, which is for Microsoft Edge, we reduced the ability for a content process to talk to the kernel. Why would we do that? Well, what we found over time is attackers were very annoyed and disrupted by this concept of sandboxing. It's not just Microsoft that's driving sandboxing. Chrome has an effective sandbox. Adobe has a sandbox. Microsoft Office has a sandbox. And so attackers need, if they're going to sort of perform their nefarious deeds on your machine, they need a way to get out of this sandbox. And so if you look at the kernel being a monolithic space with a lot of potential targets, traditionally over time, what we've seen attackers do is build kernel exploits. So the kind of model there has been get code execution into a sandbox process, then build a second exploit to the kernel to escape that sandbox process. So in order to counter that threat and that growing trend that we're seeing, in the Edge process, we actually simply prevent you from calling into any kernel APIs or any kernel components that are not absolutely necessary for Edge to function. And so by doing that, we reduce significantly the opportunity for an attacker who's got code execution in the sandbox for targeting the kernel. And that's a huge boon for security. So Edge is really, for lack of a better term, cutting edge here in the sense that we've got a highly compartmentalized isolation model, as well as full kernel isolation, or kernel isolation for Win32k, which is the most commonly attacked component. So very powerful constructs here. And then finally, if all else fails and you get through the layers of security I've talked to you previously, then we want to ship patches as quickly as possible. So how do we do that? Well, Microsoft has a very mature process for mobilizing engineering teams in the event of an in-the-wild attack or a vulnerability being responded, identified. We also have what we call URL blocking or exploit blocking capability in Internet Explorer and Edge on Windows 10. So what that means is there's actually a list that's enforced in the browser that if we know about a zero-day being hosted on a particular website or maybe a particular set of infrastructure, we can actually push out within 15 minutes a signal to all the browsers across the planet running Internet Explorer and Edge that simply block navigation to that site. So that's something we've used incredibly effectively in the past. Additionally, we have a very mature program for exchanging data securely against security partners. So if Microsoft has knowledge of in-the-wild attack, we're able to share that with various security vendors, many of which you may have products in your network. So we have a very effective and mature relationship there. And then finally, I probably don't have to tell the enterprise crowd that Microsoft can ship updates pretty well and frequently for security. So that is actually a huge boon to responding to attacks. So in conclusion, security is a lot more than simply fixing the code we write. Over time, Microsoft is working with kind of all our partners. As I said, it's not just Microsoft code, but working with Adobe, working with Intel to really, really change the game with respect to memory corruption or exploit attacks. So some of you may have heard that Intel has a proposed chip design that they're slating for a few years out that actually fundamentally prevents return-oriented programming at the chip or microprocessor level. And Microsoft's been involved in kind of providing feedback to that design. So we believe that by working with partners like Flash, Intel, and various other folks that we partner with, we think overall that we're driving the ecosystem to reach the same successful results that I've showed you here for components like Microsoft Edge, et cetera. And so let's talk just in the last couple minutes about what the results have been. So we think we've made incredibly measurable progress on improving customer safety based on all of the improved processes and technologies that I showed you here today. So the number of vulnerabilities that are exploited in Microsoft code have dramatically dropped in the last 5 years. In the last 2 years, we've had no zero-day exploits, and those are remote code execution exploits found in the wild that work against Internet Explorer 11 running on Windows 8.1, and the major delta there being Control Flow Guard. And this is a key one. Since releasing Microsoft Edge 1 year ago, we have yet to see in the wild a zero-day against Microsoft Edge, which is huge, given that we have tens of millions of people running that. We think that this is a demonstration that all of the technology and strategies that I've showed you here today have been incredibly effective. We're keeping Windows 10 and Edge up to date, and of course, our data-driven approach and our red teams consistently work to bring cutting-edge technologies. I expect I'll be back here next year talking about some of the stuff we're doing in the next version of Windows, and I can tell you, if you think this stuff is cool, wait till next year. We're really, really, really pushing the envelope with respect to exploit protection in Windows. And so with that, I'm happy to take any questions, but I did want to urge the crowd to look at if you're not part of the Windows Insider program, you should absolutely be looking at the WIP program. One extreme benefit of that is often the mitigations I was showing you and the exploit protections I was showing you today, we're testing those now. So if you get in the Windows Insider program, a lot of the things that we're developing for the next generation of Windows are there now. So if you want to kind of take them through a test drive, or you just want to run the most hardened Windows version of Windows possible, I urge you to get on the WIP program. And with that, I'll take any questions folks have. Thank you.
Hi.
Can't see you.
Over here.
Oh, there you are.
Hey. So you mentioned that Edge has protections against legacy document modes, but Edge supports enterprise mode emulation remediation. So how is Edge protecting against legacy document modes?
So the goal with the enterprise protection mode is that we should own, in the most optimized case, only internal sort of intranet sites that are within control of the kind of the demilitarized zone in a network should be rendered in that mode, in the highly optimized mode. So for example, we give enterprises the ability to set a site list that should be thrown into the enterprise mode that actually need the legacy document emulation. Those are really the only sites that we believe should be rendered there.
So different from Internet Explorer 11, where you have the Microsoft public compatibility list, Edge doesn't support that, correct?
So that's right. Edge has a public compatibility list, but it's extremely small and decreasing by day. And so I think we're down to just a few thousand sites where we'll actually, while you're in Edge, throw you to an enterprise mode.
Thank you.
Yeah.
What's the Edge usage rate? I mean, IE and Chrome are probably the best or most used browsers.
I think on Windows 10, I don't have the stats on me. There may be a public blog post or something I can point you to, but it is significant, much larger than Internet Explorer for Windows 10.
Okay. It was just,
yeah.
If it was small, then the hackers would obviously not focus on it. But just like why the Macs weren't really focused on until there was a mass.
Edge is a substantial part of our browsing market on Win 10 from all the stats I've seen. I don't want to quote you wrong stats, but it's substantial. It's for sure large enough to be a very juicy target.
Okay, thank you.
Sorry, I didn't catch the first couple slides of
Sure.
your presentation, so I just wanted to know like your name and like contact information, any kind of like channels that you have. Maybe we can check out some videos that you posted or anything. Or?
Yeah, so you can check out my talk from Black Hat this year, which has even a more technical version of this. But yeah, my email is just dwest@microsoft.com. I run the Microsoft Windows Red Team, as well as the Windows Defender Advanced Threat Protection Security Research Team.
Okay, D West.
Yep, yeah. Cool, thank you.